Trigonometric substitutions. Without a doubt, one of my absolute favorite methods of integration. How you recognize it, you're going to see squares and square roots. We're going to do a substitution. You're not going to sure quite why we're doing what we're doing, but there will be an explanation eventually. So here's what we do. We're going to let x equal 3 sine theta. If you do that, then what is the derivative of x? The derivative of x, if you take the derivative of both sides, you're going to end up with derivative of x equals 3 cos theta d theta. So what we did again, we just took the derivative of both sides. That lets us know what to put in here. We have to replace all our x's. So what would x squared equal? If x is 3 sine theta, then x squared is going to be 9 sine squared theta. So replace everything over here. All your x squareds become 9 sine squared. Your dx becomes 3 cos theta d theta. Now what? It's a very famous identity you're very familiar with. Sine squared plus cos squared equals 1. If we were to multiply everything by 9, we'd have 9 sine squared plus 9 cos squared equals 9. And then what would happen if we took this to the other side? 9 minus 9 sine squared theta would equal 9 cos squared theta. That was the whole point of our substitution. We can now replace 9 minus 9 sine squared theta with 9 cos squared theta. At that point, you can take the square root. Square root of 9 is going to give us 3, and the square root of cos squared theta is going to give us cos theta. And that will get rid of that square root, which was making things really quite complicated. Now what? This 3 cosine theta is really over 1, so we'll multiply the tops together. 9 cos squared theta, leave the bottom alone, 9 sine squared theta, d theta. Get rid of your 9s. And then cos squared over sine squared, that's cotangent squared. At this point, you've simplified from something fairly complicated to something a lot easier, but we still don't know the antiderivative of cotangent squared. So let's go back and look at that identity that we had. Sine squared plus cos squared equals 1. A lot of people are pretty good at remembering that one. The other two, it's a little sketchy sometimes. So if we wanted cotangent squared, what if we were to divide this by sine squared? That would give us a cotangent squared. And of course, we're going to have to do the others the same way. So 1 plus cotangent squared will equal cosecant squared. Now, some of you might already have that memorized, so you can just write that in. So instead of cotangent squared, we would have cosecant squared theta minus 1. How does that help? We know the antiderivative of cosecant squared. What has a derivative of cosecant squared? I think derivative of cotangent is negative cosecant squared. So to end up with a positive, we have to put another negative over here. So let's figure that out one more time. If y were to equal negative cotan theta, what would the derivative be? Derivative of cotan theta is negative cosecant squared theta. Those two negatives give us the positive that we were looking for. Now, where's this theta coming from? What is the integral of 1 if your variable is theta? Some of you are a little better at this. What if it's the integral of 1 if your variable is dx, if your variable is x? So that's going to give us an x. Integral of 1 d theta gives us a theta. Now we're not done. We started with x. We've got theta. We're not finished. So how do we get back from the theta to the x? We're going to draw ourselves a triangle. We're going to go back to this line. X equals 3 sine theta. If you were to rearrange that, x over 3 would equal sine theta. So if you look at the triangle, sine theta, opposite over hypotenuse. So x over 3 equals sine theta. Then using Pythagoras, 3 squared minus x squared, take the square root, and that gives you the missing side. So one more time, sine theta was x over 3, so opposite over hypotenuse. Then Pythagoras will tell you what the missing side is. And this is a marvelous time to check if you know what you're doing, because you'll find out that this always reappears in the triangle. If it doesn't, something's gone wrong. Okay, now what? Cotangent theta. Can we calculate cotangent theta from here? I believe we can. Cotangent theta is going to be adjacent over opposite. So now we can replace cotangent theta with the root of 9 minus x squared over x. What to do with theta? Let's go back up here. You know that x over 3 is sine theta. If you were to take the arc sine of both sides of that, that would tell you what theta equals. So what are we doing now? What we're doing is taking the arc sine of this expression and the arc sine of the sine. This is going to give us theta. And on this side, we get the arc sine of x over 3. So what does our final answer look like? Instead of cotangent theta, we're going to put in the root of 9 minus x squared over x. And instead of theta, we're going to put the arc sine of x over 3. Whew, that was pretty impressive. So if you're wondering how this arc sine comes in, perhaps you remember the derivatives of the arc sines, and you remember that there's often roots and squares. So if you were to combine those two derivatives, you would find that after a fair bit of simplification, you get what you started with. So how do you know what substitution to do? Here's the key. It's all based on these trigonometric identities. The goal is to be able to reduce what's under the square root into one term. So when we had 9 minus x squared, we said, oh, we're going to be using this identity. And if we would let x equal 3 sine, then we'll be able to replace it with 9 cosine squared. If it's a positive, you're going to use a tan theta because of this identity. If it's x squared minus a squared, we're going to use a secant because of this identity. So this is something you just have to have memorized or understood. And essentially, it's knowing these 3 rules. So because we want it to look like this, you're going to use sine. This one, you're going to use tangent. This one, you're going to use secant. So let's try that with a specific example. Where's our handy chart again? If we have a squared plus x squared, that's what we've got right now, we replace x with a tan theta. And what's all this a stuff? A squared is 4. So a is 2. Let's just take another look at that. When it's a positive, a squared plus x squared, 2 squared plus x squared, you replace x with a, which was 2 tan theta. Then do exactly what we did before. Take the derivative of both sides. Derivative of 2 tan theta is 2 secant squared. If x is 2 tan theta, then x squared is going to equal 4 tan squared theta. Substitute everything you can. X squared, 4 tan squared theta. This x squared, 4 tan squared theta. Dx, 2 secant squared theta d theta. Now, we're going to want to do a substitution here, and it's based on this identity over here. If you were to multiply everything by 4, 4 secant squared would equal 4 plus 4 tan squared. And then I was a little too quick. I made that into 4 secant squared theta, and then took the square root, and that's where the 2 secant theta came from. So one more time, what happened? 4 tan squared theta plus 4. If we multiplied this by 4, it became 4 secant squared, and the square root of 4 secant squared is 2 secant. After that, simplify like crazy. So I can get rid of a 2. I can get rid of one of the secants. So what are we left with now? We have a secant theta, forgive me. Should be a theta in there. And 4 tan squared. That's pretty complicated. So we're going to replace everything with sines and cosines. Secant is 1 over cos, tan squared, sine squared over cos squared. We can get rid of one of the cosines. And at that stage, probably want to multiply top and bottom by cos theta just to get rid of that denominator. So if we do that, what happens? I think we're left with cos theta over 4 sine squared theta. This is now a u substitution. We're going to let u equal sine theta. Perhaps I'll do that over there. U would equal sine theta. Du would equal cos theta d theta. Good job, we practiced all of these. Integral then becomes 1 over 4 u to the negative 2 du. Integrate that. 1 over 4 u to the negative 1 divided by negative 1. So that's what we're doing. We're doing there. Sorry, I didn't actually write down what the integral was. So the integral 1 over 4 u, which was sine theta to the negative 1. And that's the only thing we had. So no arcsines involved in this one at all. And then once we've got to this stage, we have to go back to what did our triangle look like? And how do we replace sine theta? So this one, x is 2 tan theta. So x divided by 2 is going to equal tan theta. Tangent, opposite over adjacent. So there's the x over 2. Pythagoras tells us square the x, square the 2, add them together, take the square root. Do a little check over here. If you see that square root showing up somewhere, you know you're feeling pretty comfortable about what you're doing. And there it is. Now we're trying to find sine theta. Sine theta opposite over hypotenuse. So here's sine theta. So what would sine theta to the negative 1 equal? Sine theta to the negative 1 would equal the root of x squared plus 4 over x. So our answer then, the root of x squared plus 4 over x, and we had the quarter, so the 4 stays below, it was negative, and there's our answer. If you're really keen and enthusiastic, feel free to do a quotient rule and prove that this works. Let's do one more. X squared minus 25 over x. What is our substitution? X squared minus 5 squared. So this is our substitution. We're going to make x equal 5 secant theta. So again, it was a minus a squared. So it had to be 5 squared. So that's why we're letting x equal 5 secant theta. Derivative of both sides. Derivative of x. Derivative of secant is secant tangent. What would x squared equal in this situation? 25 secant squared theta. Okay, so let's substitute. We have to substitute an x squared, and we have to substitute an x and a dx. Okay, so x squared, 25 secant squared, minus 25. The denominator, 5 secant, and then dx was 5 secant theta tan theta. What is this going to become? 5 secant squared theta minus 25. Sorry, 25 secant squared theta minus 25. So if you multiplied everything by 25, that would become the root of 25 tan squared theta. Okay. And then 5 secant theta will disappear. Oh, that's a nice clean antiderivative we're looking at now. So our 25 tan squared theta, our tan theta d theta. So I'm just going to do that one more time, perhaps in a different color to show you what just happened. So what we did again, we said, let's reduce the 5 secant theta So they're gone. So the tan theta remains. And this became the square root of 25 tan squared theta, which of course we're going to take the square root of. And that will give us a 5 tan theta coming out of the root, which then gives us 5 tan squared. Do you know anything with the derivative of tan squared? No, I don't think I do either. So what can we replace 5 tan squared with? How about 5 secant squared theta minus 5? Or 5 multiplied by secant squared theta minus 1? Either one, doesn't actually matter. And then antiderivative of secant squared. Is that tangent? And then antiderivative of 1 is theta. And because everything was multiplied by 5, there are the 5s. Again, if you're a little confused with what just happened, if y equals 5 tan theta minus 5 theta, what's the derivative? Derivative of tan is secant squared. Derivative of 5 theta would be 5. And we're back where we started. These are thetas. We've got to go back to x. To get back to our x, we draw a triangle, put theta in the corner, look at your substitution. X equals 5 secant theta. If you were to divide both sides by 5, we know what secant theta is. Secant is adjacent over, hypotenuse over adjacent. Cosine is adjacent over hypotenuse. So secant hypotenuse over adjacent. What's the missing side then? Pythagoras would say, take that squared minus that squared, take a square root and double check your question. There it is. We're feeling pretty comfortable. All right, what do we need to get rid of this time? Tan theta. What would tan theta equal? Opposite over adjacent. So there's tan theta. And what's theta? Let's come back up here. How do we get theta by itself? We would take the arc secant of both sides. So the arc secant of x over 5 would give us the arc secant of the secant. So the arc secant of the secant is just theta, and that's the arc secant of x over 5. Okay, so down here, that's what we've got. 5 times tan theta, and then minus 5 times the arc secant of x over 5. Clean it up a little bit, and that would be our answer. Okay, so these are intense. The key to these, make sure you know what your substitutions are. Make sure you remember to take derivative of both sides and substitute for the dx. One way to check if you're doing right, after the substitution, everything needs a theta. Use your identity to change what's inside the square root to one term, and then you can take the square root of that. Combine your terms, and then you have to know your integrals. If you look at that and you say, oh, that is not one of the integrals we know, you have to realize if we're going to use the identity again, translate it to something else, and then integrate. After you've integrated, we're not done. We have to go from theta back to x, and the way we do it is we use the triangle. Okay, have fun with these. They're a fair bit of work, but after you get used to them, I hope you'll enjoy them as much as I do.